In the last lecture, we have studied about pumping lemma, where I taught you that pumping lemma is used to prove that a language is not regular. So in this lecture, we will be seeing an example where we have a language given and we will prove that this language is not regular using pumping lemma. Alright, so if you have not watched the previous lecture, I suggest you to watch it first because I have described all the rules of pumping lemma in that lecture. Okay, so here we have a language given which is a is equal to a raised to n b raised to n for all n greater than or equal to 0. So we have to prove that this language is not regular. So I've taken this example slightly in one of our previous lectures and I already told you why this language is not a regular language. This is because this language is of the form a raised to n b raised to n, which means that we can have any number of a's and followed by that we should have the same number of b's like the number of a's that we had. And why this is not regular? It is because in order to achieve this language we need to keep a count of how many a's did we have. Then only we can repeat that same number of b's. But we know that finite state machines cannot keep count of anything. So this cannot be designed using finite state machines, and all languages that cannot be designed using finite state machines are said to be non-regular. Okay, so that is a theoretical knowledge that we have, but we need to have a proof for that. So for proving that we will use our pumping lemma. Okay, so let us see how we can prove this. So we'll have the proof here. For that, let us just refer to the rules of pumping lemma that we studied in the previous lecture. So here we have the rules of pumping lemma. So it says that if a language is regular, then it need to have a pumping length, let's say p, such that any string whose length is greater than or equal to p may be divided into three parts x, y and z such that all these three conditions should be satisfied. So I've already discussed this in the last lecture, so I will not be discussing this again. So let us go straight to the steps that we need to follow in order to prove this. So in order to prove a language is not regular using pumping lemma, the following steps are to be followed. First of all, we assume that a is regular. So we assume that the language which is given is regular. And if a is regular, then it has to have a pumping length which we will call p, such that all strings longer than p can be pumped. And after that, we will take a string s such that its length is greater than or equal to p, and we will divide it into three parts x, y and z. So let us do that. So the first step is to assume that a is regular. So we assume that a is regular. Now if we assume that a is a regular language, then it need to have a pumping length. It need to have a pumping length, and let me call the pumping length p. So we have a pumping length p such that any string whose length is greater than or equal to p should be able to be pumped. Now let me choose a string which I will call s, and let's say that s is equal to a raised to p, b raised to p, where p is the pumping length. A language is of this form, so instead of n I am taking p, which is the pumping length. Now what was the next step? We need to divide this into three parts. What are they? X, y and z. Alright, now let's see how can we divide this into three parts x, y and z. So for now let me just assume that my pumping length p is equal to 7. So if my pumping length is equal to 7, so I can write this string s. How can I write it? I can write s is equal to 1, 2, 3, 4, 5, 6, 7, a 7 times, followed by 1, 2, 3, 4, 5, 6, 7, b also 7 times. Okay, now let us assume that this is our string which has pumping length of 7. Now let us see all the possible ways in which we can divide this s into three parts x, y and z. So for that, let me take first case number 1. So the case number 1 is that the y part, that is this y, is in the a part. What do I mean by this? You will be clear when I do this. So what I mean by this is, let's say we have like this 1, 2, 3, 4, 5 6 7 and 1 2 3 4 5 6 7. Okay, so this is my string and the y is in the a part. So what I mean by this is, let's assume that y is this one, this part is y. Alright, so if this is y, this will be x, and the remaining from here to the end, this will be z. Okay, so this is the first case. So we have divided it into three parts, x, y and z, and then the y part, the middle part, it is in the a part, means it contains all a's, a, these four a's. So this is how I can divide it in one way, and there is another way we can divide. How is that? Let's see case number 2. Case number 2 says that the y is in the b part. The y is in the b part. Alright, so what do I mean by this? Let's say we have 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. So now I will divide it in such a way that the y is in the b part. For that, let me take these four b's from here. Okay, this is my y, and then this whole part, this is x, and this one will be z. So y contains only b. That is the case number 2. Now case number 3, there is one more case that we can have. Case 3, it says that the y is in the a as well as b part. Now how is this? I hope you already guessed it. It is like this: 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. Now for the y to be in the both a and b part, I will choose this to be my y. 2 a's from here, 2 b's from here. This is y, and this is x, and this is z. So y has both a and b. So that is case number 3. So these are the three possible ways in which we can divide our string into three parts, x, y and z. Okay, now what do we have to do? Let us just go back and look again. So we have divided s into x, y and z. Now we have to show that x, y raised to I, z does not belong to a for some I. So let us do this. Okay, so coming to the first case, let me draw a line here and let us do this. Case number 1. So for the first case, let's take any x, y, I, z. So here let me take my I to be 2. That means x, y square, z. That means I have to repeat my y part twice. So this is the first case I am looking at. So what is my x? X is a. And what is my y? Y contains 4 a's. 1 2 3 4, and I have to do it twice. That means again I have to repeat y. 1 2 3 4. Alright, then z. Z contains 1a and 7 b's. 1a and 1 2 3 4 5 6 7. Okay, so we get this string. Now we have to see if does this string lie in our language A or not. So let us count how many a's we have here. 1 2 3 4 5 6 7 8 9 10 11. We have 11 a's and how many b's? 7 b's. So 11 and 7. So the number of a's and the number of b's are not equal. So in our language, the number of a's should be equal to number of b's. So this string does not lie in our language. Alright, this string does not lie in our language for case number 1. Now let's try the same thing for case number 2. Let me take x, y raised to I, z, and let me choose my I to be 2. So I have x, y square, z. And what is x? X contains 7 a's and 2 b's. 1 2 3 4 5 6 7 and 2 B's, and y contains 4 B's. 1 2 3 4, and I have y square. That means I have to repeat y once more. 1 2 3 4, and then z is only 1 B. Now let's count again how many A's and B's we have. We have 1 2 3 4 5 6 7 A's, and how many B's? 1 2 3 4 5 6 7 8 9 10 11. We have 11 number of B's. Again, the number of A's and B's are not equal, so even this does not lie in our language. Alright, so let's do the same thing for case number 3. I take S Y I Z and I choose my I to be 2. Now let's see. Here X is 1 2 3 4 5 A's. 1 2 3 4 5, and Y contains 2 A's and 2 B's. 2 A's, 2 B's, and I have to repeat Y once more. 2A, 2B, and then Z contains 1 2 3 4 5 B's. 1 2 3 4 5. So here, if you before we count, you can see that this does not follow the pattern A raised to n, B raised to n. See, here we have A's and followed by 2 B's, and again there are A's and B's, so it is not following this pattern. So this also does not lie in our language. So we proved that when we take X, Y, I, Z and taking I to be 2, all this does not lie in our language. So let us turn back to our rules once more. Show that none of this can satisfy all the 3 pumping conditions at the same time. So we saw that this condition cannot be satisfied. So we have taken X, Y raised to I, Z, and we showed that it does not belong to A. So it will be regular only when it belongs to A. So we have shown that it does not belong to A, hence it is not regular. So we can also show that these conditions are also not satisfied. Let us see condition number 3. Condition number 3 says that length of X, Y should be less than or equal to P. Let us see if that was satisfying or not. Length of XY should be less than or equal to P, and in our case P was 7. So let us see in case number 1, what is the length of X and Y together? 1 2 3 4 5 6. So case number 1 satisfies because 6 is less than or equal to 7. What about case number 2? X and Y. X contains how many? 1 2 3 4 5 6 7 8 9, and along with Y 10 11 12 13. So 13 is not less than or equal to 7, so it does not satisfy here. And if you check here also X and Y together 1 2 3 4 5 6 7 8 9, yeah, it's 9. So 9 is not less than or equal to 7. Even the third condition also is not satisfied. So we saw that those conditions cannot be satisfied when we divide our S into 3 parts, X, Y, and Z. If you see the rules, we see that once we satisfy that all these conditions cannot be satisfied, that means S cannot be pumped. That is a contradiction to our assumption that A is regular. So we assume that A is regular, but since it is not satisfying these conditions, it shows that it cannot be pumped, and hence we have proved that the language A is not regular using pumping lemma. So I hope that was clear to you. You can practice more examples, and I will also be discussing some more examples of this in the coming lectures. So thank you for watching, and see you in the next one.